Thanks, everybody.
Up next, we have Mark Tyneway, who is an engineer with Optimism Public Benefit Corporation. Optimism, I don't think needs an introduction, but just for people who might not know, it is one of the main layer 2 solutions for scaling Ethereum with a technology called optimistic rollups. So Mark, I don't know if you want to turn on your video, and there you go. All right, take it away.
Well, hey, thanks, Tim. Thanks for having me today. Gonna share my screen now. Cool. So like Tim said, my name is Mark, and I'm from Optimistic Ethereum. And you can reach me either on Twitter or there's my GitHub handle down there on the bottom. Probably the best places to reach out to me. Cool. So real quick, just we'll give a walkthrough. What is a rollup, right? A rollup is it's kind of this way to increase the throughput of a blockchain. And you do this by decoupling the execution from the consensus. Because stateful blockchains, they usually do a lot of execution on chain, and all that execution is expensive. So the idea is that you basically just use L1 as a data availability layer, and then the L1 is responsible for consensus, and then you have the L2 that does the execution. And some neat things about this is that users can opt in to performing the execution. There can be many rollups, and users can choose which rollups they want to execute and have the state for. This also kind of decouples the runtime from the layer 1. So there's many different kind of state transition functions and many different data structures that you can define for a rollup. For example, you can create like a UTXO based rollup on Ethereum if you wanted to. And then another neat fact, it kind of like decouples the governance, because L1s, they usually have lots of value locked up in them. It's kind of risky to move too quickly. There's a lot of stakeholders. It's more difficult to get consensus around particular types of upgrades. So you kind of get this decoupled governance, and you can kind of choose to add upgrades at a different pace or focus on different types of applications. Cool. So there's really like two types of rollups. There's like optimistic rollups and zero knowledge rollups. So Optimism is an optimistic rollup. And basically an optimistic rollup is it uses L1 to make the transactions and the corresponding state roots available. Well, Optimism does, because you can have a different, different kind of data model. But basically an optimistic rollup, the state transitions are valid when there's an absence of a fraud proof during some amount of time. And basically the transactions are considered final if there's no fraud proof that is posted kind of during the fraud proof window. Cool. So optimistic Ethereum in particular, it's an EVM based optimistic rollup. And the philosophy of optimistic Ethereum is to be as close to Ethereum 1x as possible, but just increase the throughput. And we want to be backwards compatible as we can be. And this will help with the transition to ETH2, because the first couple of phases of ETH2 are really about just consensus over data, and it's like sharded data. So we're hoping that Optimism will be able to allow for the execution in the early phases of ETH2 before there's sharded execution. And Optimism is based on a sequencer architecture. So there's basically a permissioned like write-only node, and then all the other nodes are like read-only nodes. And the sequencer is kind of responsible for keeping the network alive and accepting transactions from users. And we have some live deployments right now. We are on a permissioned mainnet right now with synthetics, and that has been going pretty well. We're working towards adding synth trading very shortly over the next couple of weeks, and we're also on Kovan. And we're working towards opening up mainnet to more projects. We just have, we're working on like our test coverage and making things more reliable. Cool. So at a high level, this is the architecture of the system, right? So we have the sequencer, and the sequencer accepts transactions from the users. And then the sequencer will take all those transactions and batch them up and then submit them to L1. And the verifiers will listen to L1 and basically pull in those transactions and execute them off chain. And then the sequencer is also responsible for posting the state roots that correspond with the transactions. And then the verifier can take its locally computed state roots and compare them to the state roots that were posted to the chain. And basically the protocol assumes that the state roots are correct, assuming that there is no fraud proof. And to make the system work, the sequencer needs to post a bond with the state roots so that the amount of, then anyone that submits a fraud proof basically gets that bond. And so that means that the bond must be larger than the cost of executing the fraud proof. So to make sure that you want to have like the most capital efficient kind of system, you want to have a cheap as possible fraud proof. And then the users, they can send the transactions directly to the sequencer. And they basically, the sequencer tries to provide better user experience than say layer one. So the sequencer will confirm your transaction instantly. But there's a little bit of a trade-off because like in theory, if the sequencer is running in like a jurisdiction that requires them to like follow certain laws, they might like have to censor you. So if you want to get around that, then you can then send your transaction directly to layer one, which we know sending transactions directly to layer one is censorship resistant. There's a way to send a transaction to a particular contract on L1 that will actually call a contract on L2. So it's kind of like this meta transaction thing. So that at a high level, that's the architecture. Cool. So I think thinking about the sequencer as a service provider like really kind of helps my mental model. And I try to think of it as like the layer one contracts are your service level agreement with the sequencer. And the sequencer is bound by the rules of the layer one contracts. Because generally the sequencer has a lot of power. The sequencer can really choose the ordering of the transactions. And like Optimism is a public benefit corporation. So we do not plan on, say, like extracting MEV from ordering the transactions in a particular way. But basically, we need to figure out the primitives that are needed to basically prevent a malicious sequencer from, going rogue and capturing too much MEV and being bad for users. So it's really just about setting up the game in the ecosystem. So when you're running a sequencer, the sequencer, like I said before, will accept transactions directly from users. And then it also ingests transactions, L1 to L2 transactions. And then it will, after it executes the transactions, it'll make them available on layer 1 with the corresponding state roots. And then it also has to post the bond, which I talked a little bit about earlier. And it is responsible for the ordering of the transactions. So there's some interesting kind of mechanism design around the right to order transactions, because ordering transactions, as we've learned, is a very, very valuable thing. So there's this idea of like an MEV auction where the sequencer can order off or auction off the rights to order the next set of transactions. And this is not implemented yet, but this is kind of just like a research idea. And we think that this could be a way that the sequencer can operate in kind of like a transparent way. And the idea would be that a tax would be collected from these auctions. And we believe that this tax could bring in an insane amount of money. And we would want to redirect this towards solving like the tragedy of the commons, basically like funding open source software and other things that like traditionally get neglected. So like funding client development, tooling, paying developers to work on kind of just common things that are used by everyone. Okay, so then there's we also have some ideas on how to kind of make the user experience 10 to 100 times better than, say, sending transactions to L1. So right now, when you send a transaction to layer 1, the gas prices can like swing crazily, and you might end up with a bunch of transactions stuck in the mempool, and it's kind of like annoying to like have to go back through and boost the gas prices. So there's some interesting things that you can kind of do with a sequencer that allow you to basically give instant transaction confirmation. So I mentioned the bond before, where the sequencer needs to post a bond with the state root, and somebody can submit a fraud proof and then they get the bond if it's valid fraud proof. So the idea is that the sequencer could actually, as soon as you send your transaction to the sequencer could actually return with a commitment to the particular index in which your transaction will be included. Because you can just think of Optimism really is just like a list of transactions. So the sequencer could commit to you instantly the exact index of the transaction that the transaction will be batched up in when the sequencer submits the batch to layer 1. And if the user notices that the transaction was not included at that exact index, then the user could submit a fraud proof and take the bond. This hasn't been implemented yet, but this is something that we're talking about in the future, basically to like kind of give an optimistic instant confirmation. And then another thing that we've been talking about is kind of doing these fraud-proof based batch validity conditions. So right now, kind of there's basically 2 rules that a batch must abide by in the Optimism protocol. And that is the timestamps and block numbers in the L2 OVM must be monotonic. So you can't have time go backwards and you can't have block numbers go down. And basically, in theory, we can add more things to kind of the fraud proof rather than just like the state transition function being incorrect. We could also add in, say, the sequencer could commit to not extracting MEV in a particular way. And somebody could submit a proof that MEV was extracted in a particular way, and then they could get the bond. And this just requires a MEV taxonomy. So we need to come up with a way to define different types of MEV, and we need to be able to observe them on chain. And we need to be able to do it in a way where people can't like fake it. And because like, you know, you could define like a sandwich attack as, you know, 3 transactions, but then people might just start like sticking an arbitrary additional transaction in. And I'll define like sandwich if anyone doesn't know. It's basically somebody sees like a big trade on Uniswap or something. So they like front run with a buy right before like a big buy, right? And they get like a guaranteed kind of the price goes up because of like slippage or something. And then they just like they add a sell right afterwards. So they kind of like sandwich a big buy and they kind of get like a guaranteed profit of like the spread. So if we say created a scheme like this and we defined sandwiches as like, you know, there has to be 3 transactions, then people would just start creating like sandwiches with 4 transactions and it would kind of get around it. So this is still kind of like an open research problem that we're thinking about. Cool. So I think that you could think about sequencers as a service provider, and sequencers want to provide the best user experience. So what that means is they will give you instant transaction confirmations. There's no priority gas auctions. There's no public mempool. You just send your transaction directly to the sequencer and it confirms it. I could see sequencers in the future providing kind of key management for their users, and also providing like regulatory and tax tools. This is kind of just like the idea of a sequencer creating like a vertical integration of like the Web3 kind of blockchain internet experience, where they kind of provide you know, the Web3 versions of a lot of the things that we have today. Whether it's like login, they do your KYC, they kind of give you blockchain search. Cool. So I talked about the sequencer a bunch. There's also the verifier. And the verifier is like a key part of the system that is required for this security. And you really only need one verifier to keep the system secure, but hopefully more people run verifiers. So basically the idea of a verifier is you listen to the L1 contracts and you pull in the transactions that the sequencer is posting to the L1 contracts and you execute them. And after you execute the contracts and you basically have all the L2 state locally, and then you're able to compare the state roots that you've computed locally against the state roots that are posted to the L1 contracts. And if you see that there's a mismatch in the state roots, then you can submit you know, a fraud proof. And I think that in practice, what's going to happen is I think that the miners will actually, because there's like this whole thing where like people that really believe in zero knowledge rollups, which are like, it's a really cool technology. they sometimes will say that there's a problem with optimistic rollups where basically you have to worry about the miners censoring the fraud proof. Because if the miners censor the fraud proof, then it's the absence of a fraud proof that determines validity. So if the fraud proof is censored, then in theory, some money could be stolen. And but I think what's going to happen is in practice is that the miners will censor the fraud proofs when they're sent by users, but they will just include the fraud proofs themselves with gas price 0 transactions, because miners are starting to get smarter about MEV. So basically, they'll just include the transaction themselves directly in their own block, and just claim the bond that was posted. And it's kind of, if you think about it, it's kind of like a gas efficiency or like capital efficiency. Only one transaction can really, what I'm trying to say is that the fraud proof is like racy. If many people are trying to execute the fraud proof at the same time, like you would have like transactions that end up reverting. So if the miner just does it themselves, it actually saves gas, and you don't end up with a bunch of reverted transactions in the block. Cool. So I have 2 little pictures of tweets here. So let's look at the one on the left first. So like I said before, because the sequencer has like ultimate control of transaction ordering, this tweet by Patrick, there are 2 solutions to reduce the sequencer's power: smart contract design to limit MEV and order fairness of the consensus protocol. For example, randomize it. So I'm really interested in smart contract design to limit MEV. I do think that in the future, we will have basically like a toolkit of kind of primitives that people will just like import into their contracts that will help to limit MEV. So if anybody has any like ideas or projects that they're working on, I would definitely love to connect about that. And then the other thing is like order fairness of the consensus protocol. So this is kind of one approach to say like limit MEV, like, so basically in the MEV world, there's kind of 2 philosophies. There's kind of like the MEV exists and we need to basically the miners should extract and the developers should try to build things that prevent. And then the other side is that like MEV is bad, and at the consensus level, like we should try to prevent it. So this like order fairness of the consensus protocol, that's kind of like the fair sequencing. And I know that Chainlink is working on something. There's like their scientists are working on like a consensus protocol that kind of is meant to be fair sequencing. And I think that Arbitrum is going to be adding it to their thing, like their rollup in the long term. So then, and then on the right side, let's take a look at this one. So basically, this is just, we got Greg saying that if your L2 uses an L1 client for execution, you will not outscale the L1 you're attempting to scale. So, and then we have James stepping in saying that there's a constant factor increase in throughput, that it's probably reasonable. And then Greg comes back saying that the biggest issue is state bloat, which I agree with 100%. State bloat is a very large problem. It's really hard to get away from. We have like Binance Smart Chain, who has increased the gas throughput by like a factor of 10x, and they're going to be hitting the issues if they already aren't hitting the issues of kind of state bloat. And it's definitely like a problem that Optimism will face because we are compatible with Ethereum. And it's, but there are kind of research ideas to solve it. So basically, Vitalik came out with this proposal recently. Basically, it's a solution for state bloat. And kind of the idea is like it's state expiry. And the idea is that there's kind of epochs. And basically, you have to prove the state from a previous epoch to like pull it into the next epoch. So each epoch, the state tree is like erased. And then you have to like, prove inclusion in a previous epoch to like bring it into the new one. And then that way, the state can kind of be trimmed periodically. And, Optimism in other like, chains that have high gas throughput are like highly incentivized to implement these types of things. So if you think that this is an interesting problem, definitely hit me up because we like need people to like help build these things. So I do think that this is a problem that Ethereum will eventually like hit, and Optimism will just hit it first probably. So hopefully we can like all solve it together. Okay. So one question that I get a lot is, what about a malicious sequencer? So we've tried to build things into our system that basically try to prevent a sequencer from going too malicious. Okay, so I talked about this a little bit before, but the sequencer could, in theory, censor calls to certain contracts. So there has to be a way to send transactions permissionlessly to the L2 state. So the idea is that you can call this Enqueue function, and then basically call this Enqueue function on L1, then the transaction will be pulled in by the sequencer and it will be applied to the state. And if the sequencer does not pull in and apply to the state, then it'll end up halting the chain. And then anybody will be able to append it to the state in a batch if like enough time passes and the sequencer isn't pulling it in. So you can kind of like race the sequencer to like applying it to the state. So we also have this thing where like the sequencer can front run. So if you're sending transactions directly to the sequencer, they could, in theory, front run your transactions. So this kind of comes back to the design your smart contract in a way where it like is resistant to MEV capture. So we gave this primitive where you can get the L1 message sender. So in this, you can basically do this in an L2 contract. And the idea is that you can determine if the transaction was sent directly to the sequencer or if it was like an L1 to L2 transaction. And you can basically make it so that certain things on L2 that are protected by this modifier, they can only be called by an L1 to L2 transaction. And then if the sequencer wanted to front run you, then it would turn into a priority yes auction, similarly to like how people do priority gas auctions on L1 in the public mempool today. And just to note that Optimism is a public benefit corporation. So we have no intention to like make tons of money by running a sequencer. We're really just literally our sequencer is open source and we literally just execute transactions like first come, first serve. We just like send transactions and we'll execute them. So the sequencer could, in theory, just like use, do like Web 2 things and just like sell information before it has been submitted to L1. So it's important. We've tried to build our system in a way where the information is highly available. And we're working with some infrastructure providers to make sure that users will be able to get all of the sequencer data as fast as possible. And then we're also trying to build the system in a way where in the future, we can kind of decentralize who is running the sequencer, and we can create a competitive ecosystem of sequencers where kind of like the competitive market forces can make sure that there's no like vendor lock-in, and that users can opt in to choosing the sequencer that is providing the best service. And this will like kind of force sequencers to innovate over time. And this will give users like options so that they can, like they can vote for who their sequencer is, or they can kind of exit and go to a different sequencer. Okay, so I mentioned this a little bit earlier, but I saw this really cool tweet like yesterday or the day before, talking about kind of this protocol to protect users from MEV. So my questions are, what are the primitives for an on-chain toolbox of basically tools to protect users from MEV? And this is really useful because we kind of need this to keep the power of the sequencer in check. And will future applications like all use these primitives? And I do think they will.
Hey, Mark, sorry to interrupt, but just a 5-minute warning, just because in the interest of time, there's
cool. Yeah.
And then also we have a lot of questions, so. Thanks.
Okay, awesome. Yeah. All right. So I'll just like go through, I'll skip a slide and I'll just go to this real quick. Okay. So basically, getting closer to the implementation. So it's really important for the L2 execution and the L1 execution to be deterministic. So basically what we've done is we've virtualized the EVM inside of the EVM. So we have this execution manager. And this execution manager basically tracks the EVM context. And basically to deploy contracts to Optimism, you have to use our fork of the Optimism compiler, which basically what it does is it replaces any stateful opcode with a call to the execution manager. And this allows us to have the determinism. So you can run the contract that runs on the L2. It can run on L1 in a deterministic manner. And basically we have the safety checker that's deployed that all the contracts have to run through. And it'll basically determine if your contract is using any unsafe opcodes that could like break the determinism. Cool. So yeah, so, and I'll just end with a little bit of philosophy before answering any questions. So I think that it's really important to build things that act as a balance against the growing wealth inequality, because we're just seeing, things are accelerating towards, the 1% becoming like, the 0.01% and like, just all of the money kind of funneling to like fewer and fewer people. So yeah, that's kind of just like a personal philosophy. Cool. So I'm open to questions.
Thank you for that, Mark. That was phenomenal. Just noticed also you put the sovereign individual like book cover at the beginning of the slide. I love the book. So so there's a couple of questions. I mean, Rickmu, you kind of had a lot of conversations around it. I don't know if you want to try and just unmute and just ask the question directly. It might be easier.
Hi, can you hear me?
Yep.
Yes.
I mean, the crux of my question was more of, so you can imagine a universe where everyone's using rollups and rollups are working awesome. And as a result, any person who lies gets caught immediately. Therefore, no one will ever lie because there's no value in lying, which means that there's now no money to be made by verifiers to keep verifying because they're never going to get paid because they're not finding any frauds. So how do you continue to incentivize the verifiers to exist and keep on trucking?
Oh, that's a good question. So basically, anybody that wants to run kind of like an instant withdrawal scheme, which MakerDAO has like announced that they're planning on kind of building this, they will need to run a verifier. So basically, the idea is that for instant withdrawal, you're able to off-chain verify that the state root does match and that it's not fraudulent. And then you can then accept the withdrawal, and you can, on L1, you can basically say, withdraw to me, and I will instantly give you I'll instantly give you value on L1 as soon as I'm able to verify that the state roots match. And because of that, because the desire for the instant withdrawals, there will always be verifiers. Does that make sense?
It makes sense. I just wonder how. I agree, it makes sense that that's what should happen, but I do feel like a lot of the things in optimism are kind of like, we expect the universe to drift in this direction, and as long as it does, we're good. And I mean, that's my only concern is like, yes, that's my concern. Yes, that answer makes sense. In a world where people want instant withdrawals and instant withdrawals continue being a thing. So actually, there's a question that somebody asked me by accident through direct message, and maybe I'll just forward along because it's kind of related. Do you have to run a verifier for instant withdrawals, or is there a way to trustlessly offload that to someone else?
You do need a verifier to do the trustless withdrawal, unless you just want to trust the state root is correct. I would recommend anyone that wants to do an instant withdrawal to compare the state roots before they kind of send the funds on L1. Otherwise, you can get double spent, basically. And if you rely on someone else, you're basically relying on that other person not lying. But note that you really only need one verifier to secure the whole network. Ideally, we have many more than one. I do think that there's a world where miners also run verifiers because as soon as there's a fraud proof, like it's in their incentive to include it. And I do understand if you're like, if it's kind of like this like in theory thing that is securing the network. But we're seeing in practice that MakerDAO has publicly announced that they're planning to run this instant withdrawal scheme.
So one quick question with that then is there's no need whatsoever for miners to run a verifier, right? Because the second someone else publishes it, they can just steal it without actually doing the work themselves.
That's a good point. If assuming that the miner, that is under the assumption that, so somebody else publishes the fraud proof to the public transaction pool, then all the miners can like see it.
It's probably almost like guaranteed that it's more valuable to not run a miner and just snipe those than it is to actually run a verifier. Unless running a verifier is incredibly cheap, but I don't expect that to be the case. Anyways, I'll let someone else ask questions.
Cool.
Yeah, at this point, I think so there's a question from Anish, and then there's also a question from Emma. So just because we do have two more speakers, Mark, if you'd be able to answer them in the chat, then that'd be cool. But thank you so much for the presentation.
Cool. Yeah. Thank you for the space.
Appreciate it.